We'll make do. Don't worry about him. Every man for himself. Induction.
What are you bring
Please, I have a test today.
I don't have.
I have a test. And 36 emails I need to reply to.
Don't worry. I can help you be more.
Continue. You got this? Induction. Yep. Sean! Come on.
Be a good boy.
Yeah, be a good boy. Okay. Ready?
Yes.
Continue. Induction. So last time we were looking at the conductor, current carrying conductor in a magnetic field, and we saw how to make the DC motor. Yep. Okay. So let's continue now. We have seen that a moving charge in a magnetic field will experience a force. But what happens if we move the magnetic field? So something very interesting happens here. Last time we moved the current in the magnetic field, and the current made a magnetic field and would react using, what did we say, the left-hand rule. So the magnetic field, the current, and the force acts upward. But now, what about if we apply a force to move the magnetic field or to move the current? Yeah, we increase or decrease or change the voltage. In other words, by moving a magnetic field, by changing a magnetic field, we can cause a current to appear and measure it. Yeah? This is actually very useful because it means by simply moving a magnet inside of a conductor, we can actually cause a current. The moment we stop the magnet, we move the magnet and then we stop the magnet, then you will see the current will reduce back down to zero. So the magnetic field must constantly be moving, and then when we stop it, we see the current goes back to zero. This phenomenon is called electromagnetic induction. It's producing a current by the use of a magnet. I would like you to draw this diagram. It's a very simple but very important diagram.
That one? That's what you believe.
Yeah, this one. Well, I obviously include them for a reason. Well, this one is really simple. It's a pipe with a wire and a voltmeter, and you stick a magnet in it. Not complicated. Oh, you're thinking about this way too much now. It doesn't need to be that great.
Wow, this is the best photo. I don't know.
Wow.
Back.
Okay.
You would not have a physics essay again. No, I told you this. You only have a lab report. First you must do the labs, then you will write the report. Huh? I explained about this already. It was unfair because your English and physics knowledge isn't advanced enough to ask you to write a 1200-word essay in week 4. But they make me do it, so I do it.
So we need it advanced level of physics. We should think about our essay.
But you must understand, KJ, I have no choice in the matter. It's not a me choice. This is what I'm told to do.
Yeah,
I do say every year, I think it's unfair to my students, and I would like you instead to do a presentation. But they won't listen to me. My ideal coursework would be, coursework 1 would be the labs, with the lab report, and coursework 2 would be a presentation on the labs. This, to me, would be perfect, and you can do both of them in semester 2. But I have no power. I'm just simply a physics teacher. I do not design the course.
But the presentation requires more English.
No, you can score higher in a presentation than an essay, because it's not just about your English, it's about demonstrating you understood and communicating and all of this. No, writing an essay is much harder to get an A in.
Can you see our coursework 1 essay? Can you see?
No.
I want to see.
No, it's best if you forget about it, trust me. Okay, no, forget. Coursework what?
What?
What? It only starts at 2. Right. Note, while the magnetic field is moving, a voltage will register, as I said. So, precisely, electromagnetic induction is the production of an EMF, a voltage, across a conductor exposed to a changing magnetic field. This is the precise definition of it, if you can write this down. Right, Jerry, right. Any sweets left?
Not there, sorry.
No, I wanted more cola bottles.
I don't like this. Then where is your birthday?
June 17th.
Oh, sorry. Oh, that was my dad.
Interesting. Although he's probably older than me.
Yeah, I'm done.
June 17th? Big deal. How old is your dad?
54.
Oh my goodness, he's younger than me.
Of course, younger than you. How are you?
I use advanced nanotechnology and past 100 now.
How old are you?
I keep forgetting, actually. I need a calculator. I don't keep track of my age. It's not something I keep track of. Can't answer that in physics, sorry. Maybe you could answer that in EAP. No, ghosts. No.
UFO.
UFOs? More interesting, but no UFOs, I'm afraid. Sorry. Yeah, the time is perhaps a little bit redundant. That's why I put it into brackets. By time varying, I mean as time passes, the magnetic field changes. You might say, well, how else could it be varying? Clearly this is what I mean, but some people might interpret a varying magnetic field just to mean that it's stronger at one point and weaker at another point. I'm just trying to make sure not to cause any confusion, that as time passes it changes, not that it just changes in different positions. Okay, continue?
Yeah.
Yep. Bruce? No?
Can they close windows half?
Hmm?
Can they close the windows half?
Yeah, let's close one of the windows, please. Okay, continue? Continue? So we have two laws regarding how the induction produces the voltage and in what way. So the first one's called Lenz's law, which tells us the direction of the induced current. In other words, is it flowing forwards or backwards? And Lenz's law says that if an induced current flows, its direction is always opposite to the change which produces it. The best way to see that is with a picture. Here, as I put the magnet in here, the north, as I put the north end in here, the current will flow out from this end. Ding, that way. As I remove the magnet from the coil, so if I remove it, then the current will flow in, so it's flowing in this direction, so ding, points the other way. Okay, so the change, it's going in, so the current comes out. It's opposite. It's coming out, so the current goes in. This is called Lenz's law. You can either write this, or you can either draw this. Your choice. I think I know which one you'll pick.
Thought. Yeah.
Artist?
Yeah.
No, write or draw.
So how they repel from the magnet, like the poles between the coils and the magnet.
No, that end is not, that's just indicating the north goes in that side. Not that there's a pole there. Likewise here, I'm indicating that, I suppose you're saying that the south came out this side.
Oh,
Or does the pole change because of the direction of the current?
That north and south business is a bit confusing. It's actually quite confusing. The only thing that matters is whether you're pulling the magnet in or out. Yes?
Direction of current affects the pole.
Now these north and south?
just like what we said last time.
Yeah, no, true, but I should really delete these because huh?
Because
But there is no.
that small explanation up there, saying the coil attracts the magnet, because the south is there, so the south pulls the north
Should we try the teacher?
as it moves.
Wait, there'll be you're saying there's a magnetic field here?
No. The presence of the magnet
Yeah?
reduces the current.
Yes.
Because there's a current.
There's a magnetic field?
Yes.
Yes. So there is a magnetic field here. Yeah. I don't care about that. What I'm just trying to get you to understand from Lenz's law is the direction of the current. But yes, if there is a current flowing here, which there will be, then we know that this is a solenoid which will produce a magnetic field, which we talked about. But I don't care about that. I care about the direction of the current, that's all. So I know I want to delete this, not because it's not there, but because it's causing, it's distracting from the point I'm trying to make, which is the direction of the current.
Is it possible that using this created coil, the magnet to move without you having that?
Oh, no, a force is required. Because it's kind of like using the left-hand law, whereby you provide the force and you provide the magnetic field and you get a current in response. Whereas previously we provided the magnetic field, we provided the current, and we got a force in response. So of the three, you must provide two and you'll get the third. So we've seen provide these two, you get this. Provide these two and you get this. So you can also have a force and move the current, and that will produce a magnetic field. Can I continue now? Yeah? What are you doing, drawing or writing?
Oh.
Yeah? Okay. Continue. So, we know a moving magnetic field will cause a current to flow in a conductor, and we know the direction of the current is to oppose the field. But we do not know how to calculate the voltage. So we know the direction of the voltage in the last picture. We know which way the current will flow. But what we don't know is how much current we will get. So this is where we need our second law today, called Faraday's law, which tells us how much current, how much voltage we will get. And Faraday's law says that the EMF, the voltage that you get, is equal to minus N, and what's the N here? Is the number of turns, the number of surfaces. This, on the top, what do you think this is? The change in the flux, and this, the time that change took place. Now the only purpose of the minus is Lenz's law. The minus is just to tell me that the current will be in the opposite direction of the change of the magnetic field. So if the magnetic field is moving in the positive direction, then the current is moving in the negative direction. So the only purpose of the minus here is to remind me of Lenz's law. The minus, in fact, is just Lenz's law, stating the opposite direction rule. Okay, so this is Faraday's law. This will be obviously key for this lesson today.
So in question, we no need to write minus,
Again,
right?
a bit like with Hooke's law, the minus is there to tell me the direction. Often the question just cares about the voltage, and if they did care about the direction, that would be a separate question for 1 mark. This is normally what happens. Can I continue? Do you have Faraday's law? Yeah? Okay. So, if we move a magnetic field around a conductor, or a conductor around a magnetic field, then can we use this to generate power? So last time we saw that by moving a current we would get a force, and we can use this to make a motor. Today we ask, can we move the magnetic field to make a current? In other words, to make electricity. And the answer is yes, which is called the AC generator. And this is what the picture looks like. Now when you look at it at first, it looks really, really similar to the DC motor, but there are some important differences. Say again? Yeah, what can you see that's different? The key difference is in the DC motor we had carbon rings like this, whereas for the AC generator we have 2 separate rings, and one of these rings is attached to one end of the armature, and this one is here you can see this ring is attached to the blue half of the armature. And instead of having a power supply here, we have a resistor that we're trying to power, and we have to provide a force. So we have to turn this. This moves inside the magnetic field, which will make the current. Now, I said earlier, if we move a magnet, we make a current. And I want you to understand that that's the same thing as if we don't move the magnet but move the conductor. You understand? If I move the magnet, I can make a current in the conductor. If I don't move the magnet but instead move the conductor, it's the same effect. So that's what's happening here. It's much easier to move the conductor than to move these giant magnets. So rather than spinning the magnets around, we spin the armature around, and it has the same effect as moving the magnets around. This will cause a current here, which will show up in this picture here. Now what's very interesting about this is that, I think we'll get on to that. Remember that the voltage is equal to this according to Faraday. But remember what the flux equals. That's equal to BA. And let's forget about the minus N for a moment, okay? Because what's the N here? The number of wire loops, and the minus?
The
Direction. So just forget about that for a moment. So how does the BA change in this picture? Well, remember, the normal to the plane, which is rotating, makes an angle theta with the field. In other words, from the lesson we had earlier, we have to put a cos theta in. Remember, we have BA cos theta. So we get BA cos theta. But how does cos theta change? In other words, what's the rate of change of cos theta? how does cos theta change? What's the rate of change of cos theta? Because B, think about this. B, does it change or is it constant? It's constant. The A, it's constant. It's only the theta that's actually changing. So the BA is a constant. BA is constant. So really we just need to know how the cos changes. How does cos change? In other words, what's the rate of change of cos?
0 pi.
No.
1
No. What's the rate of change of cos? What is the derivative of cos? How does cos change? What's its derivative?
Sine.
Sine. So the way cos changes, the speed at which cos changes is sine. So that's sine.
Yeah.
So that means the voltage will have a sine shape to it. So this is what the graph of the voltage will look like. At the beginning, when the armature is in this position, vertical, we have no voltage. Then as it rotates, we'll get a voltage. But then it will decrease again, and then it will flip direction. Okay? So there's two things I need you to draw. Before we draw this, I need you to try and draw this, please. I cannot. I need to find the picture and... There we go. How's that?
I want white to...
Yeah, well, first draw. Yes, again. Because they might ask you to draw this in the exam. And what is this picture called? AC generator.
Is that a maximum? Can you zoom in again?
Say again?
Can you zoom in?
Zoom in more. Goodness. I don't know.
So hot. So is this still using left hand rule?
No, actually, it's not. Good question. It seems like it's the same situation as before, so we still should use the left-hand rule. No, instead of using the left-hand rule for this,
Right hand rule.
it's going to be right.
Why?
Just is. Well, not quite. It's like asking F equals MA, why?
Why?
Good question. Why?
Oh, it is. So, like, for example, if you ask why F equals MA, well, there's not really a why. That's just the description of how the force behaves. So, why do we use the right hand and not the left hand here? That is just a description of how the current behaves when it's induced. Oh, come on, it's not bad.
We have to draw in that.
Yes, yes, I have seen them ask you to draw a DC motor or an AC generator.
You suffer it?
Can you simplify like the two balls?
Dude, it's just two rings and two boxes.
No, it's not like that.
It's a
Peak.
So easy.
What?
Oh yeah, do we have to make it 3D?
Of course. I want to slip on some 3D glasses and see this.
3D.
I'm just going to look at my nice cup now. Okay, where you draw this. I do like this yellow bird on it.
You change the cup every day.
I bought new cups. I got these in the Euro
Well,
shop.
why not just get a bottle? And you
I
can
have to clean it.
Gosh,
I'm so busy. I'm so busy. I haven't even got time to clean a cup.
Yeah, you're a physics teacher. Is it a topic?
I'm a physics teacher, not an eco warrior.
then you don't wash it, like keep using it. Because it's still...
This? This goes in the bin now.
No, I mean, if you buy the...
I have to wash it. That needs energy too.
Yes, green.
I don't want green. Too much work to be green. I have a hybrid car. That's green enough.
No.
And I have no kids. That's even more green. Do you know how much food they eat and how much energy you have to use cleaning them? Yeah. I must have saved tons of CO2 every year. Okay, continue now. You should have drawn that by now. I'll go back to the slide in a moment. Monica? Come on, let's go. Okay, there's magnets, brush and slip rings.
How about the black color when the power supply?
No, you know what that is. That's a resistor. But you know this. And you know what this is. What's this? What's this? A current.
But it's big, right? But it changes direction.
Yeah, it does, which we'll get on to now in the next slide. Okay, so we've seen that if I try and show you here with my pad here, when the armature begins in this position, there's no voltage, and then it starts to rotate, and this produces a voltage. Now, what's interesting is the voltage that's produced increases and then decreases and then reverses direction. So it's actually going to make a sine graph. But of course we knew that because we said, according to the formula, a derivative of cos is a sine. So it's not really surprising that we get it this way. Yeah. This is what the graph looks like. Now this means though, when the current comes out, then it'll quickly change directions and then change directions again. This is quite different to what we had in semester 1. In semester 1 we had what's called a DC current. The current always travels in one direction. But now we have what's called an AC current, which means the current is changing direction. In fact, that's what comes out here. These are AC currents.
Why not DC?
What do you mean, why not DC? I don't understand your question.
Why don't we use DC instead?
Because when we generate power in the power plant, it already comes out as AC.
Oh, for the transformer.
No.
To convert?
No.
Oh,
No. When electricity is generated, the generator produces AC. You would need another machine to change this into DC. This is quite wasteful. It's much simpler to just provide AC in the home. It means it's the responsibility of the machine to convert it to DC. It needs DC. Although some appliances will work regardless if it's AC or DC. The simplest being a light bulb. The light bulb doesn't care about the direction. Unless maybe it's an LED light bulb. And we saw before with some of the LED lights that if you reverse the direction of the current, you can get this. Remember that? Yeah. So for an old-fashioned light bulb, it does not care about the direction of the current. A simple electric heater does not care about the direction of the current. My laptop will care about the direction of the current and will convert it into a DC.
yeah. Why not DC first?
What do you mean?
Why not?
I just told you. Because it comes out as AC when you make it.
So why? Why when I make it from AC first?
Because I just explained it in this slide. Yeah.
But also the transformer, right? Because the transformer cannot convert DC.
The transformer we haven't done yet.
Oh.
And you're correct, the transformer can only convert AC as well. So it has a second advantage, as you said. Although transformer is a simple device anyway, so yeah.
Right.
Yes. Instead of. No. Is it okay, continue?
Do we need a
formula dA cos.
No, I'm just trying to explain why the graph is the shape it is. Interestingly, the voltage increases and decreases and changes direction. That's what happens here. Does anybody know how many times per second this happens?
0.1.
How many times per second it changes direction?
1.
No?
No.
50.
Yes. Well, that was a big jump to go from 1 to 50. It was 150. Per second, it will change directions 50 times.
Wow.
This tells me 50 times. In the power plant, the wheel is spinning 50 hertz, 50 rotations per second. Yeah. This is the speed of the generator, 50 hertz. So it means the current here changes direction 50 times. Yeah. Well, it depends. If it's by a waterfall, it could be a waterfall that's spinning the wheel. If it's a wind farm, it'll be a wind turbine. If it's a coal power plant, it'll be steam from burning the coal.
What about nuclear?
Nuclear is steam as well. The nuclear energy heats steam to spin the turbine. Yeah, continue. Yeah. We had a look at this already. So what is exactly AC current? The definition is AC current is a current in which the flow of electron charge reverses direction, whereas in DC current, it's only in one direction. Okay. Can you make note of that, please? Don't want to write it, Bruce?
No, I can't.
Oh, okay. You can't see it. All right.
Clear.
Okay.
Teacher, good luck in your exam.
I don't need to look, but thanks.
Do you need like revision or something?
No, I'm okay. Look, don't worry. I just want to do a little bit more, okay? We'll break this into 2 lessons because there's quite a lot in this. The next thing is, if I look back at the last picture here, what should we say the voltage is? I mean, if it keeps changing, what value should we use?
0, plus and minus.
Well,
Minus.
not really, because if we said this is 0, then it would make you think it's okay to stick your finger in it. So we shouldn't say 0.
Undefined.
We shouldn't, again, for the same reason. I would like to know what the voltage is here, so that if I stick my finger in it, I know how quickly I'll die. Yeah, so like, my question is, should we use the maximum value? Or maybe we should use some kind of middle value?
Maximum.
Yeah, we shouldn't really use the maximum voltage, because it's only there at the maximum briefly. So maybe we should use some kind of mid-value. Well, this is getting a little bit better. But the most sensible thing, of course, is to use what the average voltage is. So, like, for example, this will go 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 maybe, and then 90, 80, 70, 60, 50, and all the way down to minus 100. So should we use the average? Yeah, we should use the average, except we don't care about the minus, because the minus is just the direction. So if the voltage is a minus, it will still kill you. So this will still be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and we'll still consider this 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we should use the average and of all these numbers. But there's a very, very, very nice way to work out the average. We have this rule that lets us work out the average if we know the maximum. If we know the maximum, the limits, we can actually get the average voltage by simply dividing by the square root of 2. This is actually a way to work out the average voltage. If we take the maximum voltage and divide by root 2, and this is very, very useful. The reason is, and you could actually test it out yourself. I could give you a sine voltage graph, I could give you all the values, and you could average it, and you would see you would get the same answers taking the maximum divided by root 2. The proof requires calculus which is not on the course. Did you write this formula down? And if you're wondering, a rough reason KJ can give you is why root 2 and not 2? Well, in fact, you would only use 2 if the graph was like this. If you had a voltage graph which looked like this, then the average value of the maximum and 0 would be exactly halfway in the middle if it's linear. The reason for the root 2 is because the shape is actually not linear, it's curved. And the curve on the top half is not identical to the curve in the bottom half, so the average should not be in the middle. Where I got the root 2 from requires calculus, but just as a rough explanation of why I'd say it's not 2. It's not 2 because it's not linear. And the upper half of the curve is different in shape to the lower half of the curve. Finally, do we have a handy way to figure out which way the induced current will flow? Yes, we do. We have what's called the right-hand rule. No, last time was the left-hand rule. So in the right-hand rule, you have the current, you have the field. Sorry, you have the motion, and by the motion I mean, you know, when you turn it, which way is the force being applied. So if I have a wheel, you know, and I have to pull it up here, that the motion will be up. The field here and the current, which way we have it, the induced current flowing. It is Fleming's right-hand rule. So we'll just finish by drawing that. Once you've drawn that, we'll finish.
Isn't it done with FBI?
It is, except with the right hand.
Left-hand rule was for electric.
Left-hand rule, DC motor. Right-hand rule, AC generator. Right-hand grip rule was for the magnetic field around a current. We have a rule like the right-hand rule that Monica was telling us about for the magnetic field around a solenoid, but I do not believe this is tested on the exam. I can check this, but I think for the exam they don't ask this. I'll double check the syllabus and see.
Don't worry about it.
Got my left-hand rule, got my right-hand rule.
Yeah.
I mean, isn't it good we don't have any architecture major?
What?
I mean, our drawings are not good, so it's really good that we don't have architecture vendors.
But you have a word. Look at this top. This is.
Did you draw that?
Yes.
This one. Look at your top. Yeah.